Hey, this is your favorite German compositor Shitty, and I'm the host of. Welcome back on Split the Diff, and this is part 2 of the episode about the transform node, and it's all about production techniques. Today we will have a look at how we can use this node unconventionally. We will check out how we can dissolve between two transform nodes, how we can convert a 2D camshake into 3D space, how we can merge multiple transform nodes into one, lens or focus breathing, chromatic aberration, and how we can orient 2D objects automatically. Please use the chapter markers to jump around, and if you've learned something, please like and subscribe. Are you ready? Let's go! When we move an image out of frame, it's literally out of the picture. But sometimes we might find ourselves in the need of a repetitive transformation, an object going out on one side of the frame, but entering it from the other side again. I'll show you an easy way to set that up, but let's have a look at some math that we can use for this purpose. The modulus operation, written with a percentage sign, this function performs a division by treating all numbers as integers, so only full numbers, and outputs the remainder. For example, 4 modulo 2 equals 0 because 2 fits into 4 2 times. 5 modulo 2 outputs 1 because 2 fits into 5 2 times, and then we are left with a remainder of 1. 19 modulo 5 outputs 4 since 5 fits in 3 times, which equals 15, so we are left with 4. If we swap those numbers so the first number is smaller than the second, we always end up with the first number. This is because the second number doesn't fit into the first one, so the product is 0. We have to add the first number to 0 in order to reach the value of the first number again. What we can see here is that we can use this operation to count up to a certain value, and when we reach it, the remainder jumps back to 0 and starts counting up again. This is exactly what we are looking for. What we want is that our pixel moves out of frame, and when it reaches a certain point, we want it to jump back and come back into screen from the other side. I've set up a group containing multiple transforms. The node that we control with the user interface is this one, not connected to anything. First, we split up our transforms in X and Y. This first transform node takes care of our initial movement. We start with values of 0 for X and 0 for Y. What we want is to have basically a copy of whatever we see in our resolution outside of our frame. So we will use our modulus operation to check what is in frame and what moves outside. The expression on this first transform, that is supposed to control our visible X movement directly, is set up the following way. The raw state of our expression is our format width modulo our format width, which will always give us 0. By adding the X translation on the left side, we will end up with exactly this number. In this case 0, because we haven't moved anything yet. If we give it a value of 30 pixels, it outputs 30 pixels. That's exactly what we want right now for the beginning. The next node does exactly the same thing for the Y direction. Now comes the interesting part. We need to create a copy of what we see in frame for outside of our frame. We start with Y. This node uses the same expression as the other transform responsible for Y movement, but it offsets the image in negative Y direction. On the left side, we have our offset version of X, translating it into negative X space. We then need a corresponding transform responsible for the Y translation in this negative X space, and one that is offset down into negative Y. If we merge them all together, we get our anticipated result. To whichever side we move the object out of frame, it will come back into frame from the opposite side, even to the point where we have all 4 copies visible in frame. Let's look at this expression again. If we move the object 800 pixels on the x-axis, the transform node that mirrors our controller transform node moves out of frame. If we look at the transform node that we set up as a copy in negative x space, it now moves into frame. If I set everything back to 0, we get 0 modulo our format width, which is 0, since there is no remainder. We offset it by the negative width, so it's out of frame. By increasing the x value, the number on the left is our remainder, so we are increasing our value, stepping up from minus 2048 to minus 2047 2046, and so on. If we reach 2048 in our controller node, the formula is 2048 modulo 2048, which suddenly equals 0. With the offset of minus 2048, we suddenly land back out of frame again, exactly what we want. This happens on all sides now. Of course, you don't have to use all copies. For example, I can deactivate 2 copies to get the illusion that the object is moving into the upper right corner and comes back in the lower left. As an additional step, I'm checking the dimensions of the incoming bounding box and make sure that the output of this group does not exceed those. I can't just blindly copy the bounding box since the incoming object might be really small. I want the box to expand over the whole frame if necessary, but not exceed the initial dimensions outside of frame. What I also want to mention is that we can perform this repetitive transformation not only once, but rather infinitive. We know we can blend 2 images into another, but what about 2 individual transformations? When we dissolve between 2 images, meaning we move the slider between 0 and 1, what actually happens is that input 1 gets multiplied with this value, while input 0 gets multiplied with 1 minus this value. It is basically an inverse operation. They then get added together. If we take that knowledge and apply it to knob values of other nodes, we can accomplish the same thing. I have this square and one transform moves it from left to right, while the other one moves it from right to left. I created a master transform node which collects all the knobs of the 2 transforms. I added my control dissolve knob. And lastly, I have a third section with transform knobs which gives me the output of the new combined, or better blended values. I'm using the same expression that I showed you before, multiplying translate x of the second input with my dissolve value, multiplying translate x of the first input with 1 minus the dissolve value, and then I add those values together. I do this for all the knobs, and then I link my output values to the actual transform knobs of this combined transform node. Of course, I can skip that third section and do the calculations right away in the actual knobs, but it's nice to get that overview under one tab. That's how it looks like with an animated dissolve. In this example, I'm also using different sizes and rotation. The dissolve is animated again between frames 20 and 80. It gives us a smooth transition. Now we know how to blend between transformations, but what if we want to add them all up into one transform node? In part 1 of this episode, we talked about how Nuke actually processes transformations internally. That is with matrix multiplication. If you haven't watched the first part yet, or you need to refresh your memory, please check out the video, or specifically the chapter about matrices, available on my channel. Also, if you haven't heard of concatenation yet or are not sure how it works, please catch up first with part 1. Every type of transformation, whether it is translation, rotation, scaling or skewing, uses its own transformation matrix. They all get multiplied in a specific order and only then multiplied with every pixel or vector of our image. You can see how complex those operations can become, and this is only a simplified view on it. I didn't take the additional translations into account that are needed for some operations like rotation and scaling to first offset the image based on its pivot, so the operation can be performed around the origin. If you maintain concatenation, the matrix multiplication continues across those nodes. I showed you how we can access and view or print the transform matrix of nodes that do output these. If you only perform translations, the matrix values seem to look quite straightforward. After complex operations, though, the values can look very cryptic. This is because they ran through various multiplications. In general, you can say that those values here resemble translations, including offsetting the pivots. The rows and columns here collect our values for rotation, scaling, and skewing. Everything seems so intertwined that it seems like we would never be able to deconstruct those values into their individual operations anymore. And this is partly true. Extracting the combined translation value is no problem. For rotation, scale, and skew, though, we will be able to extract individual values, but they will not necessarily match the series of operations how they actually happened. They will give us the same visual output, though. The process of deconstructing a matrix is also called decomposition. There are various different approaches and functions out there. Let's have a look at one of them. The formulas can be a bit complex and overwhelming. Let's check how we can set up a Python script with the help of those formulas so we can automate the whole process. First, we have to import math since we will use some functions of this module. I'm collecting the selected transform nodes in a list and also determine how many items I have selected. We have to check for the center or pivot value of our last node since we will need this later to properly offset our translate vectors. I create a new matrix object and set it to its identity state. Again, if this doesn't look familiar, please check the matrix chapter of part 1 of this episode. Next, I create the transform node that will house our combined matrix operations. I also create a vector object which I will need to convert the translate vectors from our matrix structure into actual vectors or pixel coordinates. I'm using a while loop to go through all my selected transform nodes and their matrix knobs so I can perform a matrix multiplication one by one. For this loop I needed to know exactly how many nodes I had selected. I end up with one final matrix as a result. If we look at our equations again, we notice that we only really need 4 positions out of that matrix in order to perform this decomposition. Position A, B, E, and F. M and N are also important, but that gets easily resolved for us with the following transform method for our matrix. By using the vector that we created earlier as an argument, we convert those values into actual pixel values that we can assign to the translate knobs of our combined transform node. This is also the time to perform the offset for our center in case our pivot is not at 0, 0. For rotation, scale, and skew x, we basically follow the equations for this decomposition. It is important to say that we have to convert our result for rotation from radians to degrees before we assign it to the rotation knob of our combined transform node. Now you might wonder, what happened to skew y? Like I said, a decomposition might not perfectly mirror the actual operation values, but the visual output will match. In the case of this composition, if we perform skew y operations in one or more of our stacked transform nodes, this will be represented by a combination of the other operations. So, I have this stack of transforms here, all performing their individual set of operations. Let's run our script here and it spits out one single transform node. If we compare the results, they match. You can see that the knob values might all be different, but that's unfortunately what we'll have to deal with. And of course you can expand that script by adding functions that perform those calculations for every single frame in case we are dealing with animated transforms. We can then paste the whole curve into our combined transform node. Let's focus a little bit on what we can accomplish with rotation. When we place the pivot away from the object we would like to rotate, the orientation of the object will change. A way to avoid this is to use the pivot of another transform centered on the object and link up the rotation values by an expression. By using the additive inverse of the rotation value, we are able to maintain the orientation of the cube. What if our cube is translated and keyframe animated along a path? Is there a way to align our object in a way that it is always facing its path, like a car racing on a track? Trigonometry makes it possible. It's time to revisit what we have learned in the first part of this episode. Imagine those are the points that make up our path. Our cube moves by being shifted right on the x-axis and up on the y-axis. So in a way we have to consider 3 lengths, which gives us a triangle for every frame of movement. In part 1 of this episode we learned how to calculate angles of triangles. Let's have a look at the 3 common formulas. We name the sides of a triangle with a right angle the following. The side opposite of the right angle is called hypotenuse. The side opposite of the angle we would like to calculate is called opposite, and the remaining side alongside the angle is the adjacent. The sine of an angle is the ratio of the opposite and the hypotenuse, while the cosine is the ratio of the adjacent and the hypotenuse. The tangent of an angle is the ratio of the opposite and the adjacent. Now, this sounds very interesting since we might be able to find the lengths of x and y that our cube moves. To get the actual angle, we have to calculate the inverse of the tangent, which is also called the arctangent, of the ratio of the opposite and adjacent. It would be great if there's a way to find out how much in x and y our cube moves in the next frame. We would be able to calculate the orientation angle to face this path. Well, fortunately in Nuke there is an expression that we can use for this purpose. The derivative. Let me show you how this works. This cube is keyframe animated in a linear way. Between frames 1 and 20 it moves 20 pixels to the right and 10 pixels up. 2 pixels to the right per frame and 1 pixel up per frame. And this is the value that the derivative function spits out for us. It is a measure of the rate at which the value for x and y changes. I set up those custom knobs with the derivative split up for x and y. If we look at the graph and check those values, we can clearly see how it works. The value of the current frame shows us how much the cube will move the next frame. If we hit the top of the curve, where it is flat for a few frames, the value switches to 0, before it goes back to minus value since our values are declining. We can use this function now for our tangent function since this gives us the two sides of the triangle we need. For this example, I stored our opposite and adjacent values in those custom knobs. Then I'll use the arctangent function, and since this will output the result in radians, we have to convert to degrees. I'll use an if statement to check for frames with no increase or decrease in x and or y values, for which we will use the angle calculated for the previous frame. And this is the result. I added a custom knob for a secondary rotation so we can change the overall orientation of the cube without interfering with the automatic alignment. Another interesting function is called arctangent2, meaning it takes two arguments, specifically x and y coordinates. It will spit out an angle between the positive x-axis and the ray to the point xy. I rotate this point here as a test. I've set up the arctangent2 formula for whatever point I pick. If I place it right at our point here, the formula spits out the angle. With this information we can adjust the angle of this triangle and therefore the alignment of this ray. For example, we can use it to horizontally or vertically align an input. I have this checkerboard here which is rotated at a certain angle that is not known. I have set up a transform node with some custom knobs. I will be able to define or pick 2 points. I will calculate the difference for the x values and the difference for the y values. Since we want to calculate the angle, we need to offset the values in a way that the ray starts in the origin of the coordinate system, so we can rotate around it. I use the arctangent2 function on this result and need to convert it to degrees again. So let me place those points along the line here. When we check the result after the transform node with our arctangent2 function, the checkerboard is aligned horizontally. Focus or lens breathing is the term to describe the small change in focal length of a lens when adjusting the focus. This is caused by very subtle shifts of the lens elements within the camera. The effect is a change in image size. A simplified way of visualizing and calculating what is happening inside a lens is by using the thin lens equation. Since lenses are very complex constructs and differ not only between different types but also sometimes between different versions of the same model, this setup and formula takes a simplified approach on things by only using a single lens. We can use the equation to solve missing parts of the formula like focal length, the distance between lens and object, or lens and image sensor. It says that when we focus at infinity, we get a focused representation of the image right at our focal length behind our lens. That's where those light rays cross each other. So let's say this would be a 24mm lens, then the image would be in focus 24mm behind our lens. The lens would move, so its distance to the image plane or sensor would be exactly this, one focal length. For objects closer to the camera, the lens has to move in order to have the focused image sit right on the image plane. And you might know this from a magnifying glass. When we move the lens further away, in this case from the sensor, magnification is the result. Like I said, lenses these days are all very complex and consist of multiple lens elements, and they all work differently. So instead of moving the whole lens set, only individual elements might shift around and so on. But this formula is a good starting point to create a generic control for us to match this effect. The effect we want to accomplish is a magnification, so we want to scale our image based on the distance between lens and sensor. First, we can set our focal length and focus distance here. Since focus breathing only happens when we change the focal distance, you want to animate that value based on your camera data. If we know the focal length of our camera and distance we are focusing at, we can use our thin lens equation to calculate the lens sensor distance. That is exactly what I'm doing with this knob expression here. Since our focal length is mostly given in millimeters, I have another knob set up in which I will convert the focus distance to millimeter. If you're working with footage that you haven't shot yourself and they provide you with on-set data, you never know what measuring systems they use. So that way it's quick and easy to convert from inch or meters, for example. To create a normalized value of 1, we divide our lens distance by the focal length. That proves again that our lens is in its default scale state when the focus distance has the same length as the focal length. If we now set the focus distance closer to camera, you can see our value increasing, because the values of focal distance and focal length move away from each other, increasing the ratio. That would match exactly what the thin lens equation says. But a lot of the times we focus on objects and actors close to our camera. If we would set the value to 50 centimeters in front of the camera, our object that we run through this node would already get a magnification. Usually we are placing our objects correctly and start our effect from the initial state. That's why I added this reference frame knob. We will use this value to normalize our scale factor on this frame, meaning the scale factor here will be 1 and then move relative from this frame on. We do this calculation in our final output knob by setting the following expression. We divide our current scale factor by that same value that we calculated on our reference frame. If we are looking at exactly this frame right now, the result will be 1 and then change for the surrounding frames. I added an overall multiplier and control for aspect ratio, which I only use for scaling in width, in case we are working with anamorphic images. Okay, let's have a look at our shot again. I've measured all the distances and placed 2 checkerboards in Nuke's 3D space so they would sit on this table. I'm feeding our camera with the information for the focus distance, which is changing throughout the shot, matching what is going on in the plate. Those values also go into my PG bokeh nodes, which I'm using to do a proper defocus for me. This is how those objects look like with rect defocus only, if I merge them with the plate. You can understand the problem we are facing. It's time for our focus breathing setup. We link the focus distance from our camera again so we don't have to animate this knob ourselves again, and the formulas do the job for us. That's how the elements look with our setup applied. If we merge this with our plate, we will be rewarded with a quite good result. Let's talk about a very typical situation we sometimes face while working on a shot. It's close to getting finalized, but the shot lacks some dynamic. Chances are big you will be asked to add some cam shake in comp. This might help regarding the missing dynamic, but we face the following problem. The image is flat and has no depth, hence everything in the image will shake the same way. In real life, when we move our camera around, things in the foreground will be more affected than things in the background. This is called parallax and gives us a sense of depth. That's why we have 2 eyes, and when we move around, our brain can make us understand if things are near or far away. While it is definitely smart to work with a flat pre-comped image to play with and test camera shakes because of performance reasons, it doesn't mean that we can't go back to 3D to apply it. To be fair, the please add camera shake comment might be added at the end of your schedule for this shot, and there's no time to go back to lighting and render everything with a new, now shaking camera. But you might still be able to place your renders on cards in Nuke's 3D space and make use of some proper parallax for your elements. Now the challenging part is the following. While our 2D camera shake is basically a transform node, it will work in pixels. In 3D space, we work in units though. I'll show you a way to convert your post move from 2D pixels to 3D units. I've set up a quick expression on this transform, basically stealing it from Nuke's camera shake node. This shake is basically using a FBM, fractional Brownian motion function. There are also other functions you can use, like noise, which is basically a Perlin noise, or turbulence. I will not talk about different expressions for camera shakes in this episode, since there will be a future episode about Nuke expressions in general. Something interesting though, if you need a bit of a visual representation of what those functions and their individual components do, you can load in Nuke's noise node. If I set it to FBM to match the function that we use here, you can see that we find variables of our equation here too. Things like octaves, linearity, gain, or X and Y amplitudes can be found here. Sometimes it's nice to see in a visual way what changing those values would do to our curve and its details. So, this is the shake that I created as a test here, applied to a checkerboard, which gives us a nice quick playback speed. I've set up the scene in Nuke's 3D space by dropping some simple geometry into different depths. If captured by a static camera, we will get this result. By adding our camera shake, the shot might look a bit more dynamic, but like I said, everything is moving the same. Let's move things into 3D. Now you might think, okay, I can just link my translate X and Y values to a 3D camera. Rotation would work, since whether it's 2D or 3D will work in degrees. If I connect the translate values though, it will look like this. That is because 10 pixels we move in our 2D image will now be 10 units in 3D space. Nuke's 3D space is measured in centimeters, so we would be moving 10 centimeters. But how do I know how many centimeters match 1 pixel of my rendered image? We can use what we've learned in the previous chapter about lenses. The field of view at a distance of 1 focal length away from our lens will match the dimensions of our image plane or sensor. So let's say our camera sensor has a width of 24 mm and we are using a focal length of 40 mm. Then our field of view, 40 mm in front of our lens, would be equal to 24 mm, the width of the sensor. With this knowledge, we know that 20 mm in front of our lens, so half of it, would have a field of view of half the sensor width, 12 mm, and so on. The tricky part here is that the shot or scene we are shaking has objects in it that represent different depths. They all have different distances to the camera lens. So we need to decide what our reference depth is. That way the position of the object at this depth will match 100% with our 2D shake, while the other objects will move fractions or multiples of it based on real parallax. I automated this process already by using Python, but I'll show you exactly what I did. I will use an axis to capture the shake and convert it into 3D units so I can plug it into a camera. I'm not using it on the camera directly, since the actual shot camera might have its own animated camera move already. We have to set our format width, since this will be important to know how many pixels in width we are working with. The equivalent in 3D space is the sensor width of our camera, which you will have to adjust for whatever specs your camera is using. And we have to set or link the focal length of our camera. First, we divide the unit width by the format width to find out how many units match 1 pixel at the distance that matches our focal length. So here, 24 mm in front of the camera. If we divide this by the focal length, 24, we know how many units we see through the camera at a distance of 1. We multiply this with the value we choose for z, since we want to know how many units we are working with at this specific depth. That's basically it. If we multiply this value with our 2D translate pixel values, we will end up with the matching values in 3D units, centimeters. Let me apply this 2D shake now to our flat rendered 3D scene, while I hook up the axis to the camera of the same setup so the shake gets applied in 3D space. I'll set my sphere as the reference point to match the 2D move, which is at a depth of 24. I'll choose 22 though, since 24 is where the center point of the sphere is, but I would like to use the front part of the sphere to match the transform. If we compare those two outputs, we can see that the sphere position is matching. but we get a much nicer and realistic look of a three-dimensional move on the right side. I actually added a second shake with a higher frequency but smaller amplitude to my test to add a little bit more complexity. We can use our script from earlier to combine both those transforms into one, and then we convert it to our axes. Let's say we also use an animated camera for our 3D setup. If we now compare both outputs, there still is a difference, but it is not as noticeable anymore, since the animated camera already gives us a feeling of more depth. So you'll have to decide when it does make sense to switch back to 3D and when you can keep it simple in 2D. Chromatic aberration is a common lens defect. The red, green and blue channels are not properly aligned to each other, which results in color fringing, especially in contrasty areas. There are two different types of chromatic aberration. The first one is called axial chromatic aberration. The reason for this defect is that the lens causes the color components of the light to focus in different depths relative to the image sensor. As we can see here, the blue light focuses right on our image plane, while green focuses in front of the sensor, so the green component will be slightly blurred. It's even more extreme for the red channel in our example here. When we look straight at the sensor or image, the light ray gets broken up like this, and it can happen all over the image. Since this fringing originates locally from every individual light ray, we cannot really reproduce this type of chromatic aberration with an overall transform operation. This has to be achieved with convolution, which we will probably talk about in a future episode. What we can recreate though is the second type of this lens defect, lateral chromatic aberration. This time all color components focus perfectly on our image plane, but only in the center. The light rays that hit the sensor further outside and especially around the edges get laterally displaced or smeared. So when we look at the image, then the red, green and blue channels might line up perfectly in the middle, but the more we go towards the edges of the frame, the more they spread apart. And now you can see why we can mimic this effect with the transform node. We can achieve this by scaling our color components with different factors. Let's have a look at a simple setup. First step is to split up our color channels. I'm using one node with custom knobs to control everything. You can obviously also put everything in a group, but I kept it open for visibility. We have control over every individual scale. Since chromatic aberration as well as lenses in general tend to soften the image towards the edges, I also added some blur nodes. I added a second transform node which we can use for overall shifts in X and Y or rotation. I will show you in a bit how it works. Green runs in the middle and we shuffle in the red and blue channels, but of course it doesn't have to be in that order. Let us play around with the values a bit. Since we know that the center might not really be affected by lateral chromatic aberration, I'm using a radial mask to key-mix in the effect. Of course, this can be changed based on how bad the defect of the lens actually is. We can scale our channels and blur them individually as well as overall. This section here gives us the option to shift the effect around in case the lens shows different characteristics for different sides of the image. I can play with the weights to determine how much each channel gets affected by this. Also, I can select if I wish certain channels to inverse the movement. Since I have the checkbox for blue selected, it will automatically move to the left into negative X direction, while red shifts over to the right. If I change the weight for a channel, it will move less than the others. Same goes for rotation. If you want to have an isolated look at your adjustments, you can simply use a merge with a difference operation, comparing the node tree before and after the treatment. An important thing to mention, if we use this setup for an image that is not covering up the whole frame, we need to keep an eye out for the alpha channel. Since we will shift the channels also across the alpha edge, we want our alpha channel to also be affected by scaling and shifting. But it would be wrong to do this with a solid alpha. Since we might only shift one color channel, the corresponding alpha should reflect that. By using a multiply set to 0.3333 before I split the channels, I make sure that the alpha for every one of our 3 channels has a value of 1 divided by 3. We will add up the alphas when we shuffle back our colors, so we will end up with an alpha of 1 matching the input image, but the shifted or scaled edges will now have a semi-transparent alpha added. Okay, let's say you need to match the chromatic aberration of a plate, so you can use it for your CG or comp elements. A good way to do it is to shuffle out one channel of your plate, run that through your setup, and try to match the original plate. Here we can actually perfectly see the problem of chromatic aberration and how those 3 color channels don't line up. You can see it on the edges of the trees and how they jump from channel to channel. So, if we quickly play around with our values, we can quickly come up with a good first pass, which we can then tweak in detail to perfectly match every area of the plate. This brings today's episode to an end. I hope you enjoyed it. Please let me know in the comments if you have special ways of using the transform node, and also let me know about wishes for future episodes. I'll see you soon.